We're going to now look at ejectors. So people have heard the term multi-ejector. Didn't make sense when I first heard it. I was kind of relating it to liquid injection into a scroll compressor, things like that. It's very, very different animal. So the ejector, if I can get a close-up, that lets me aggravate Josh for a close-up. So the ejector block looks like this. We had one on the other end of the, we showed it on the other end of the system earlier. This first piece, this is going to be our screen. It's removable, serviceable filter screen. And all of the flow coming from the gas cooler will travel through this screen. And then here we have various ejector blocks, is why it's called the multi-block. That ejector inside it looks something like this, where this is your gas cooler flow. This is medium temp suction return inlet, and this is the exit to the flash tank. So that device we see on the slide, thank you, Josh. So what we see on the slide here is an ejector port. And I mentioned earlier that I like to study things until they click in my mind simply. So I'm actually going to equate this to something I think most of you will be familiar with. So entering the actual ejector itself, the device we just looked at, we've got the mass flow from the gas cooler. We've got the medium temp from the suction cases coming in the little, looks like a revolver barrel portion. And then those mix together and they exit and return to the gas tank or to the flash tank. So for me, this kind of reminds me of a wand for a pressure washer. Pressure washer wand does the exact same thing using a Venturi effect, which is kind of what we're creating here. So if we travel through this, the ejector again, we go from the gas cooler inlet. So that's our high pressure water going into the wand of the pressure washer. So we're to that point on the pressure washer wand. Then we bring in the medium temp suction from the cases, which we haven't explained yet, but we're going to. Just trust me for the moment. This is the suction return from medium temp comes in here and joins the gas cooler mass flow, which is not unlike the soap solution from the tube that drops out of your pressure washer wand. And then the two mix together through the mixing chamber here and then exit through the diffuser. Very similar to our pressure washer wand. They mix together here and then exit as a soap and water mixture. So our soap and water mixture for the pressure washer example is our gas cooler and medium temp return gas mixture. One thing to note is that similar to parallel compression, you're only going to get this effect when you're in high ambient conditions. So having said that, think of the ejector working when you've pulled the wand, the trigger on the pressure washer wand. We only get that Venturi effect when we've pulled the trigger. So that Venturi effect goes something like this. The ejector block we looked at earlier, we've got our high pressure inlet. On this example, we've got 3 off and 3 on. So we come through the ones that are open. We travel to here. At this point where they mix, we're restricting the flow. And by doing that, we create a low pressure area, and that creates our Venturi effect, like the pressure washer does, drawing the soap solution up and mixing it with the high pressure water. So when we create that low pressure, we actually create a lower pressure than our medium temp suction at 400 pounds. And that's going to cause our medium temp return gas, which we've now piped back towards the ejector block, to draw into this. They call it lift. It's going to cause a lift to bring that. It's going to come into the ejector. It goes up here and mixes with the gas cooler. Then it goes through the mixing chamber and exits and all leaves together and goes back to the flash tank / receiver. So we come to the top. This is coming from the gas cooler. We come here. We restrict the flow. We bottleneck it. That causes a low pressure situation with a Venturi effect that draws in our medium temp return gas. Then they mix together and they exit and they go together down into the flash tank. So the benefit of that looks kind of complex. You wonder, well, what's the benefit? So we talked about parallel compression and what that does. So these will always be used, just food for thought. The ejector block is always used in conjunction with parallel compression. You can have parallel compression without the ejectors, but not ejectors without parallel compressors. So again, much like the parallel compression option, you paid for all of this. It's a 60-degree day. It's not really going to do anything for you. We only got 17% flash gas at 60 degrees, and we already know that's not enough to run the parallel compressors, and we're okay running it on the medium temp because of the efficiency we get from CO2 as a refrigerant. So on that 60-degree day, you're going to get 100% of your load still going all to just the medium temp compressors, not using the parallel compression at all. One thing to note, we're showing the high pressure valve and the ejector block. Most people are doing that because they have the high pressure valve as backup, but you don't have to have the high pressure valve. But if you want to purchase it every time, we're okay with that too, obviously. So here we'll notice nothing went to parallel compressors, and the reason is we haven't pulled the wand, the trigger on the pressure washer wand. Back to that example, there's not enough pressure drop across the ejector block, and there's not enough mass flow because it's a cooler ambient. We're not running everything. We can't create the Venturi effect. And this is a new line here. This is our suction accumulator. We piped from here over to the inlet of the ejector block. Now let's look at this with a warm ambient. So now we're at 100 degrees. We're back to our 43% flash gas in the top of the tank and 57% liquid going out to serve the store. So we've already determined that sending that 43% to the plus 18 is a bad idea. We're going to move that up. And again, that flow is going to make its way over to our parallel compressors. However, since it's 100 degrees, we're using full operation of the ejector block. I spoke too soon. We're going to look at the 57% liquid right quick to help explain the ejector. So of that 57% liquid going to the evaporators, the low temp makes up about 35% of that. The medium temp is going to make up about 22% of that. So at this point, the refrigerant coming from the medium temp evaporators has a decision to make. Do I go to the plus 18 at 400 pounds, or would I go somewhere else? If we've pulled the trigger on the wand, meaning we've got high pressure drop across the ejector and we've got high mass flow, we're going to create a condition that makes that 22% go to the left on our diagram, and it's going to slowly weave its way back over to our parallel compressors. And the magic of the ejector block is this. At this point, we're now running 65% of our overall system mass flow on a plus 36 compressor. And that includes serving the plus 20 medium temp evaporators. And that only leaves 35% coming to our low temp, or to our medium temp, I'm sorry, because all it's doing now is servicing the low temp load and compressors. So at that point, with the ejector block working on a warm day in parallel compression, 65% of your overall mass flow is being handled at almost 30% better efficiency than it would be without the parallel compressors and the ejection block. So here, if you'll remember, we got 43% efficiency before, without being able to pull the 22% over. So with no ejector block, 43% efficiency, add the ejector block, you're getting 65% back up to that higher efficiency. And that's really the purpose of ejectors. This unit in particular, this big red training unit has ran, I believe it was in Jordan, at like 125 degree ambient. So the myth that transcritical CO2 and warm weather can't be friends, that's not been the case for many years. We're still trying to dispel it, but part of the effort here today is to explain this technology to try to get people to quit thinking of CO2 can't be in warm weather.